In this lesson, we're going to talk about the definition of a limit. So our learning outcomes are: use correct notation, describe the limit of a function, use a table of values to estimate the limit of a function or to identify when the limit does not exist, and use a graph to estimate the limit of a function or to identify when the limit does not exist. So if we look at a couple of different functions here, we have f of x equals x squared minus 4 over x minus 2, g of x equals the absolute value of x minus 2 over x minus 2, and h of x equals 1 over x minus 2 squared. Something these all have in common is they're not defined for x being at 2. And we see the graphs of each of these down here. So this one has a, it's not defined there. You could factor it out, and if you remember from your pre-calculus days. This one, it's for g of x equals absolute value of x minus 2 over x minus 2. It is equal to -1 until you get to 2 where it's not defined. Then after 2, it's equal to +1. And then we have this 1 over x minus 2 squared, and this would be having a vertical asymptote at x equals 2. So these are all different graphs, obviously different types of functions, but they are also functions that have that commonality that they're not defined at x equals 2. But they have some, there are ways we can work with these graphs, and that's what we're going to be talking about today. So if we look at f of x equals x squared minus 4 over x minus 2, I mean, yes, we could factor that to be, get my writing on, x minus 2 times x plus 2 over x minus 2. And if you recall from your Math 126 days, those are reduced out, leaving you essentially f of x equals x plus 2, where we have x minus 2 equals 0 as a problem. We have to keep in mind, so x equals 2, it's not defined there. It creates a hole. Creates a hole. Excuse me. Now, looking at the graph though, going from each direction, it's approaching what value, and that value is 4. So you see here it's going towards that 4, and here it's going towards that 4. Even though at x equals 2 is not defined, the limit of the function at that point is 4, because that's what it's approaching. So from this very brief and formal look at one limit, let's start to develop an intuitive definition of a limit. So our definition is here: let f of x be a function defined at all values in an open interval containing a, some value that's going to be approaching, with the possible exception of a itself. And let L be a real number if all values of the function f of x approach the real number L, as the values of x not equal to a approach the number a. Then we say that the limit of f of x as x approaches a is L. So the symbology of this is going to be right down here: limit as x approaches a of f of x is L, or you could say limit of f of x as x approaches a is L, so number L. So we're going to fill in the blank here. What do you think it's going to be? It says if the limit of f of x as x approaches a equals L, then when x is near a, the corresponding values of f of x are close, and here's a blank to fill in. We have these choices: and possibly equal, and always equal, but slightly smaller when compared, as they can be, but never equal, but slightly larger when compared. What do you think it'll be? 2L. And the answer is, drum roll, and possibly equal. It's possible that the limit is the actual value when you plug it in, but the idea of a limit is we can find it despite the value possibly not existing. So we can estimate it using a table, and we have a couple of examples here. So to evaluate x, limit of f of x as x goes to a, we begin by completing a table of functional values. So we choose two sets of x values. One set of values approaching a and is less than a, and the other one is approaching a isn't greater. So we have on the left side and on the right side. So here they're given an example. A is the specific value it's approaching. You can do a minus 0.1, a minus 0.01, a minus 0.001, and so on. On the other side, it's a plus 0.1, a plus 0.01, a plus 0.001, a plus 0.0001, and you're going to plug those values into the function as well. Now, this isn't meant to be tedious for you at all, and I'll show you how to real quickly on Desmos come up with the values using the table function. I mean, that's what I've done, but Desmos is a really good tool. Also, if you have a graphing calculator, you could put the function in your y equals, and then you can make a table and then set those values so it will calculate all that for you. It's not supposed to be a time-consuming thing. We're after seeing a trend here. So now we're going to look at what these numbers approach. So if both columns approach a common y value L, we state that the limit of f of x as x approaches a is L. We can use the following strategy to confirm the results obtained from the table, or as an alternative method. So you can graph it using a graphing calculator. You can also trace the graph and just see where the values are approaching. But we have the use of a really good tool. We have a lot of great tools that are just that weren't available a short time ago. So let's look at this first one here. The limit as x approaches 0 of sine of x over x. Now if I put 0 in there, sine of 0 is 0, and put in 0 down below, it's a 0. So I'd have 0 over 0, which isn't defined. But I can go ahead and look at Desmos, and here I've already put it in. We have y equals sine of x over x, and that's the red graph. And then I was able to do a table, so you do this plus button, and see this is table there, and allows you to add a table. And when you're doing that, it'll give you, starts off with an x1, then you do another one, it gives you an x2, and then you could type in, I typed in the sine x1 over x1. That's a critical step, is that this subscript has to match the one over here on the left. And what is easy to do is you can highlight the sine x over x and then paste it in there and then just add the subscripts. It's real simple, just you put a 1 or 2 next to the x. You don't even have to push any other buttons. It automatically makes it a subscript. So given that, what I wanted to show here is we're approaching 0. This is the green, so this is from the right. And the blue is approaching the 0 from the left. So what's happening, we're like a 0.95 or 95885, 0.973, 0.985, 0.993, 0.998, 0.999, 0.999, you see more nines there. And you can start seeing a trend, I think. I can see a trend. And on the other end, again, negative 0.58, it's 0.958, 0.9735, 0.985, 0.9933, 0.9983, 0.999, you get all these nines here now. So on both sides, and we can see graphically what's happening. I'm going to zoom in here. We can see they're approaching the same value. Now at 0, it's not defined, but both sides of this are approaching the same value. And by the way, graphing calculators and programs like Desmos or on the TI-89 or 84, they're not going to show the hole there where there is a hole because it's infinitely small. So, but we see the trend line, and we as mathematicians understand that it doesn't exist there, but it gets infinitely close. So, given that, we can say that the limit of sine of x over x as x approaches 0 is going to be 1. Even though if I plugged it in, I had 0 over 0. 0 of 0 doesn't mean it's going to be 1. That's an undefined quantity. It's indeterminate, and we can't just make these assumptions. Sometimes that might be 0, and sometimes that might be infinity, so just be aware. Let's look at the next situation. We have the limit, sorry, I didn't mean to scroll that much. Limit as x approaches 4 of a square root of x minus 2 over x minus 4. So I have another Desmos thing set up for that. So when I did this one, I just type in SQRT and then the x, and that gave me this part here, minus 2 over x minus 4. And if I could just jump back for a second, if I look at putting a 4 in there, we're talking about as it approaches 4. Put a 4 in there. Square root of 4 is 2. 2 minus 2 is 0. 4 minus 4 is 0. So that would have been 0 over 0 as well. You think this will be 1 as well? Let's find out. Okay. Back to this. So we have, I copied and pasted this down to here, and I added the 1s there, so this relates to this x1. Same thing down here, added the 2, so it relates to that x2. So on these values is 4.5, 4.4, 4.3, all the way down to 4.05, 4.01, and so on. These are looking at it from the right side, so the purple is on the right side. Then the blue here, 3.5, these are on the left side. And we look where these are going. So these values are climbing closer to, looks like 0.25 to me. These are getting closer to 0.25. So we would say that the limit here as x approaches 4 of the square root of x minus 2 over x minus 4 is going to be equal to 0.25. I'm sure someone's going to comment that, oh, you got to say the limit of the square root of x minus 2 over x minus 4 as x approaches 4. So if I've offended someone in the math community, I apologize. But that's the way the limit process works, is we look at the trend of the values and how they're approaching the value in particular. Okay, let's go ahead and go on. Another one here. The limit as limit of 1 over x minus 1 over x minus 1 as x approaches 1. Again, if you plug the 1 in there, you're going to have 1 over 1 is 1, 1 minus the 1 is 0, 1 minus 1 is 0, so you have a 0 over 0. Let's see what this might be. I also have a Desmos made for this one. There it is. And I made the tables here. And so we're approaching 1. Got these tables set up. So I have 1.05, 1.01, and so on. And if I look at these, it's approaching, let's see, negative 0.95, negative 0.99, negative 0.999, negative 0.9999. So it looks to me like that direction is going towards negative 1. And down here, it's on the other side, it's a little above, so it's negative 1.11, negative 1.01, negative 1.001, until we get to negative 1.0001. So both sides are going towards this value of 1. And it sure looks like that's how it is on the graph. Again, at 1 it would not be defined, but it's approaching that value. So we can write the limit of 1 over x minus 1 over x minus 1 as x goes to 1 equals negative 1. Both sides are going towards negative 1. Let's try another one. So this one's f of x equals e to the 3.8x minus e to the 4.3x over x. So recall our rules of exponents. We can't subtract these because, I mean, they're same base, different values. We can't do anything else with that. If I put the 0 in there, 3.8 times 0 is 0, so e to the 0 is 1. 4.3 times 0 is 0, e to the 0 is 1, so we have 1 minus 1 over 0, so we have 0 over 0 again. So they give us these values that we're supposed to come up with. So I jumped over to Desmos and made another one of these. It's kind of an interesting graph. So we're looking at the behavior as it approaches 0, so we're looking at what happens as it gets close to x being 0, so it's approaching the y-axis. And at 0.2, 0.1, 0.01, all these values, and it looks like it's getting closer and closer to negative 0.5, and it certainly seems like that's the case here. So our limit as x approaches 0 of e to the 3.8x minus e to the 4.3x over x is equal to negative 0.5. So I should say the limit of e to the 3.8x minus e to the 4.3x over x equals negative 0.5. Okay. Hopefully that seems like it's doable and it's not going to be too tedious to go through and create a table. Okay, at this point, we see from the tables that it may be just as easy, if not easier, to estimate the limit of a function by inspecting its graph, as is to estimate the limit by using a table of functional values. In the example below, we evaluate the limit exclusively by looking at the graph rather than using the table of functional values. So recall that looking at a graph, a function's value at a given x value is simply the y value at x. So here we're looking at what happens as x approaches -1. -1's right here. So as x approaches that, this graph from this direction looks like it's going towards 3. From the other direction, it's going towards 3. At that value, it's actually 4, but from each direction, it's approaching 3. So I would write the limit of g of x. They don't even tell us what g of x is because they want us to look at this on the graph. As x approaches -1, is going to be 3. Okay, there's a video. If you go through the lesson in the book, there'll be a video you can watch on this. Let's try another one. We have the graph down here. We're curious what happens as x approaches 2, so we want the limit as x approaches 2, I said it wrong again, of h of x is what? Okay, so from the right, looks like it's going towards -1. From the left, looks like it's going towards -1. So I'd say that's at -1. That's it. Okay. 2 important limits. Some rules here. So one is let a be a real number and c is a constant. The limit of x as x approaches a is equal to a. So that, like if you're saying limit of x as x approaches 3 is going to be 3. Also, if you have some constant like 5, you say the limit of 5 as x approaches 3, that's still going to be 5. That's not going to change because it's a constant. So these are just kind of showing you why that's the case. And let's talk about the existence of a limit. As we consider the limit, the next example, keep in mind that for the limit of a function to exist at a point, the functional values must approach a single real number value at that point. If the functional values do not approach a single value, then the limit does not exist. So let's talk about this limit of sine of 1 over x as x approaches 0. What's that going to be? Well, I created a table for this one as well. And here we go. This is an interesting graph. So I use the values that were approaching 0. 0.1, 0.01, 0.001, 0.0001, and so on. And what we're seeing, we have -0.544, -0.5. Okay, it looks like it's going somewhere. 0.82, that's a big jump on the other side. And then -0.3056, and then positive 0.0357, and then -0.34999. It's all over the place. Well, let's look at the other side. I went -0.5, -0.1, all the way up to -0.000001. And we're seeing the -0.9, positive 0.54, positive 0.506, -0.826, 0.305, -0.0357, positive 3.4999. Okay. Well, as I'm getting closer to 0, look at these values. I have the -0.001 and the positive 0.001. They're on opposite sides of the x-axis. So these are jumping all over the place. And if I zoom in, it's kind of funny. It almost makes me dizzy. It looks like what was that movie, Interstellar, when he's going towards the black hole and he's seeing infinity? That's what it looks like to me. So what I'm trying to get across here is, in a function like this, there's no value that both sides approach, so that our limit of sine of 1 over x as x approaches 0 does D and E does not exist. kind of interesting. Okay, I have one more to do here. And this is the limit of an absolute value of x squared minus 4 over x minus 2 as x approaches 2. So once again, let's jump over to Desmos. And so we're talking about as approaches 2. So we're looking at this value right here. And on the right side, which is these black dots here, 2.5, 2.1, 2.01, and so on, it looks like we're getting closer and closer to 4. But on the left side, as we approach 2, we have 1.5, 1.9, 1.99, and so on. We're approaching, looks like, negative 4. So these aren't approaching the same value. Therefore, this limit does not exist. So once again, I'll do the limit of the absolute value of x squared minus 4 over x minus 2 as x approaches 2 does not exist. And I want to say one other thing about this. If you're using Desmos, it's really not hard to get this absolute value. You can do ABS and then the value, or you can do the shift backslash button that's between the backspace and your enter or return button to get those. So I encourage you to spend some time in Desmos and work with it. If you get stuck on something, you can ask me. You can also pull up videos to see how it works and get some other hints. And I believe that's the end of our lesson. So hope this was a good introduction into limits. And we're going to be using limits when we get to the definition of a derivative. But we have more lessons coming up on limits. So stay tuned.